Hi boys and girls, this is lecture 8.9. Today's review topic, Extrema. Extrema are maximum and minimum values, points where a function reaches a highest or lowest value respectively. These extrema may be absolute, also called global, or relative, also called local, depending on the interval specified. Extreme value questions are not found solely in problems containing graphical representations of functions. Questions regarding maximum and minimum values also occur in problems having to do with rates, differential equations, motion, and tabular data. Thus, it's important to be skilled in determining extrema given multiple representations of functions. Classifying critical points, Part 1. On this page and the next, we're going to fill in the blank with one of these four choices: absolute max, absolute min, relative max, relative min. Number 1, a function f defined and continuous on the interval -2 less than or equal to x less than or equal to 5 has critical points or critical numbers only at x equals -1 and x equals 2. The function f has values as given in the table below. -2 and 5 are the endpoints of the interval. -1 and 2 are the only two critical numbers of the function. Therefore, these are the only candidates at which extreme values might occur. The value x equals 2 locates what value of the function? At 2, we have the function value 0, which is the lowest of the four values. So this will be an absolute minimum value. The value f of x equals 2 is what value of the function? That's here. Notice of the four function values, it is the highest. Therefore, it is the absolute maximum value of the function. Number 2. If x equals 2 is the only critical point of a function f, and f double prime of 2 is less than 0, then x equals 2 locates what value of the function? A critical point and concave down there means that we've located an absolute maximum value of the function. Number 3, if f prime of 2 equals 0, therefore is a critical number, and f prime of x changes from negative to positive at x equals 2, then x equals 2 locates what value of the function? Well, if f prime of x changes from negative to positive, that means on the original graph we would have slopes decreasing then increasing. We've located a relative minimum value of the function f. Number 4, if f prime of 2 equals 0 and f double prime of 2 is greater than 0, then x equals 2 locates what value of the function f? If f prime of 2 equals 0, it's a critical number. F double prime of 2 greater than 0 means a concave up section of the graph, meaning that we've located a local or relative minimum value at 2. Number 5, if x equals 2 is a critical point of the function f and f prime of x decreases through x equals 2, then x equals 2 locates what value of the function? To say that f prime of x decreases through x equals 2 is to say that the slope of f prime of x is negative, which means a concave down section of the graph. Therefore, at 2, we would have a relative maximum value. Number 6, if a continuous function increases throughout a closed interval, then the left endpoint of the graph of f on the interval is what point of the function? So if we have a closed interval and the function is increasing throughout the interval, then the left endpoint has to be the absolute minimum point of the function. Number 7, a student found the critical points of a function f to be x equals 2 and x equals 4 and produced the chart below. The value x equals 2 locates what value of the function? At 2, the slopes go from positive to negative. Therefore, the value x equals 2 locates a relative maximum value of the function. Number 8, if x equals 2 is the only critical point of the function f, and f double prime of 2 is 3, a positive number, then x equals 2 locates a what value of the function? Since the second derivative at 2 is positive, this indicates a concave up section of the graph. And x equals 2 is the only critical point of the function, therefore this is the absolute minimum value of the function. Classifying critical points, part 2. True or false? Number 1. A critical point or critical number of a function f of a variable x is the x-coordinate of a relative maximum or minimum value of the function. Not necessarily. Notice here I have y equals x cubed. The first derivative, y prime, equals 3x squared. If we set this equal to 0, we get a critical number at 0, yet there is no maximum or minimum value there. A better way to state this would be to say, a critical point or critical number of a function f of a variable x is possibly the x-coordinate of a relative maximum or minimum value of the function. Number 2. A continuous function on a closed interval can have only one maximum value. This is true. That maximum value may occur more than once. Notice here we have the sine function where the maximum value is 1, occurring more than once, but there will still be only one maximum value. Number 3. If f double prime of x is always positive, then the function f must have a relative minimum value. Not necessarily. Notice y equals e to the x. F double prime of x is always positive. The function is concave up on its entire domain. Yet there is no relative minimum value here. A better way to state this would be to say, if f double prime of x is always positive, and at some point on the interval f prime of x equals 0, then the function f must have a relative minimum value. Number 4. If a function f has a local minimum value at x equals c, then f prime of c must be 0. Not necessarily. Notice the absolute value function. There is a local minimum value at 0, yet f prime of 0 is not 0 because the function is not differentiable there. So a better way to state this would be to say, if a differentiable function f has a local minimum value at x equals c, then f prime of c equals 0. Number 5. If f prime of 2 equals 0 and f double prime of 2 is less than 0, then x equals 2 locates a relative maximum value of f. This is true. If you have a critical number, the slope of the first derivative is 0, and the function is concave down there, that means a relative maximum value occurs. Number 6. If f double prime of c equals 0, then x equals c is a point of inflection for the function f and cannot be the x-coordinate of a maximum or minimum point on the graph of f. This is not necessarily true. Notice the function y equals x to the fourth. The first derivative, 4x cubed. The second derivative, 12x squared. If we set the second derivative equal to 0, we get a possible point of inflection at 0. But notice it isn't a point of inflection. Furthermore, it's a local minimum value on this function. A better way to state this would be to say, if f double prime of c equals 0, then x equals c is possibly a point of inflection for the function f, and possibly it will be a maximum or minimum point on the graph of f. Number 7. If a function f is defined on a closed interval and f prime of x is greater than 0 for all x in the interval, then the absolute maximum value of the function will occur at the right endpoint of the interval. This is true. For example, let's pretend like this was a closed interval on this function. If so, the function continuously increases throughout the interval means that the absolute maximum value has to be at the right endpoint of the interval. Number 8. The absolute minimum value of a continuous function on a closed interval can occur at only one point. Not necessarily. Let's go back to our sine function. The absolute minimum value is -1 and it's occurring at more than one point. A better way to write this would be to say, there is only one absolute minimum value, but it could occur at more than one x value. Number 9. If x equals 2 is the only critical point of a function and f double prime of 2 is greater than 0, then f of 2 is the minimum value of the function. This is true. If 2 is a critical number and the function is concave up there, then there has to be a minimum value at 2. Number 10. To locate the absolute extrema of a continuous function on a closed interval, you need only compare the y values of all critical points. This is so false. Notice I have a graph here where the critical points occur and a local max and min occur. Yet, because this is a closed interval, the absolute min and the absolute max do not occur at the critical numbers. A better way to state this would be to say, to locate the absolute extrema of a continuous function on a closed interval, you must compare the y values of all critical points and endpoints. Number 11. If f prime of c equals 0 and f prime of x decreases through x equals c, then x equals c locates a local minimum value for the function. To say that f prime of x decreases through x equals c is to say that the slope of the first derivative is negative, which means it's a concave down section of the graph through x equals c. Therefore, we don't have a local minimum value, we have a local maximum value at c. Number 12. Absolute extrema of a continuous function on a closed interval can occur only at endpoints or critical points, and this is true. Here we have a non-calculator example. Given the function f of x equals negative x minus e to the 1 minus x on the closed interval 0, 3, convince me in 3 different ways that the maximum value of f of x occurs at x equals 1. This gives us an opportunity to discuss the 3 methods for identifying extrema: the candidates test, which is usually used with a closed interval, the first derivative test, and the second derivative test. We'll start with finding the first derivative. F prime of x is equal to negative 1 minus e to the 1 minus x times negative 1. This will be negative 1 plus e to the 1 minus x. Setting this equal to 0 gives us 1 equals e to the 1 minus x, and when we take the natural log of both sides, we get 0 equals 1 minus x, which means x is equal to 1, our critical number. Now let's list the candidates for extreme values in our table, the endpoints of the interval, and also the critical number. We'll need to find the function values at each of these candidates to determine the maximum value on the interval. The y values are negative e, negative 1, and negative 3 minus 1 over e squared. The largest function value is negative 1, therefore the maximum value of f of x occurs at 1. Now let's use the first derivative test. We've already set the first derivative equal to 0 and determined that the only critical number is at 1. We'll use this to set up intervals so that we can check the behavior on either side of 1 in order to determine if it's an extreme value. We'll pick a test point in each interval, and we'll find that the function is increasing to the left of 1 and decreasing to the right of 1. This means that 1 is a maximum value. Since it's the only critical number in the interval and the function is increasing from the left endpoint and decreasing to the right endpoint, we are assured that this is an absolute maximum value in the interval. Now let's use the second derivative test. The second derivative of our function will be e to the 1 minus x times the derivative of 1 minus x, which is negative 1. That means we're going to have negative e to the 1 minus x. Let's find the sign of the second derivative at our critical number in order to determine concavity there. This will tell us if it's a maximum or a minimum value. F double prime of 1 is going to be negative e to the 0, which is negative 1. Since the sign of the second derivative at x equals 1 is negative, that means we have a concave down section of the graph there, which verifies that x equals 1 is a maximum value. Here's a graphical example, also non-calculator. The graph of f prime of x shown below on the interval 0, 10 consists of a semicircle of radius 2 and a line segment meeting at the point 4, 0. The line segment has right endpoint 10, 2. Letter A. For what value of x, 0 less than x less than 10, does f have a local minimum? Justify your answer. For this, we'll need to locate our critical numbers, where f prime is 0. This is occurring at x equals 4. To the left of 4, f prime is negative. To the right of 4, f prime is positive, indicating that on the original graph, the slopes were negative, then positive. Thus, we must have gone through a minimum value at 4. Our answer, x equals 4. Why? F prime changes sign from negative to positive there. Letter B. For what value of x, 0 less than or equal to x, less than or equal to 10, does f have an absolute maximum? And justify your answer. We know that maximum values will occur at critical numbers on the interval or at the endpoints of the interval. Since there is no critical number where f prime is changing from positive to negative, which would indicate a maximum value, the absolute maximum must occur at one of the endpoints of the interval. We'll need to know the positions at 0, 4, and 10 in order to determine where the maximum value occurs. We weren't given an initial value, but let's just choose one for the purposes of comparison and say that at 0, we're at position 0. Then where were we at 4? At 4, we started at 0, but then accumulated a negative 2 pi area, 0 minus 2 pi, which means we were at negative 2 pi at x equals 4. Where were we at 10? We started at 0, we accumulated the negative 2 pi area, but we also added this positive area of the triangle, which is 6. This is negative 2 pi plus 6. Let's look at decimal approximations of these values in order to determine the maximum value. Negative 2 pi is approximately negative 6.28. And negative 2 pi plus 6 is approximately negative 0.28. The largest value occurred at 0, so f has an absolute maximum at x equals 0. Why? Because it has the greatest function value of all of the possible places where the maximum value could occur. Here we have a calculator active example involving rates. The rate in gallons per hour at which water flows into a tank over the time interval 0 less than or equal to t less than or equal to 3, where t is measured in hours, is given by r of t equals t squared sine t. And the rate in gallons per hour at which water flows out of the tank over the same time interval is given by S of t equals 2 over t plus 1 quantity squared. The tank initially holds 10 gallons of water. Letter A. When is the rate at which water flows into the tank the greatest? Justify your answer. For this, we'll need the function that models the rate at which the water is flowing into the tank. To find the greatest rate, we'll need to take the first derivative of this function and set it equal to 0. R prime of t is equal to t squared cosine t plus 2t sine t. Setting this equal to 0 yields one critical number at 2.289 hours. We know that the maximum rate can occur at the critical number or at the endpoints of the interval. So let's find the rates at each of these places in order to determine the greatest rate. At time 0, at time 2.289, and at time 3, what was the rate of the function? At time 0, the rate was 0. At time 2.289, the rate was 3.945 gallons per hour. At time 3, the rate was 3.709 gallons per hour. So the rate was greatest at time 2.289 hours. Letter B. Write an expression that represents the amount A of t of water in the tank at any given time t. This will involve an expression in which the two rate functions are working in conjunction with each other. So A of t, the amount of water in the tank at any given time, will be the initial 10 gallons plus the integral from 0 to t of the R rate function minus the S rate function, water going in minus water going out. Since the upper endpoint of integration is t for time, I'm going to substitute t with x in these expressions in the integrand. So we'll have x squared sine x minus 2 over x plus 1 quantity squared dx. And this is the expression for the amount of water in the tank at any given time. Letter C. Determine when there is the least amount of water in the tank. How much water is in the tank at this time? Show the analysis that leads to your conclusion. For this, we'll need the derivative of this expression, a prime of t. Using the fundamental theorem of calculus, this is going to be t squared sine of t minus 2 over t plus 1 quantity squared. Now let's set this equal to 0 to get our critical values. 0 equals t squared sine t minus 2 over t plus 1 quantity squared. This yields one critical value at t equals 0.867 hours. Using the first derivative test, we can determine the behavior on either side of 0.867 in order to determine if it's a maximum or a minimum value. So we'll look at 0 to 0.867 and 0.867 to 3. The function is decreasing to the left and increasing to the right, which verifies that 0.867 is a minimum value. To find out how much water was in the tank at that time, we'll evaluate this expression at 0.867. At that time, there were 9.201 gallons of water in the tank. Here we have a non-calculator example involving motion. The velocity of a particle moving on the x-axis is given by v of t equals t cubed minus 6t squared for the time interval 0 less than or equal to t less than or equal to 10. Letter A. When is the particle farthest to the left? We'll need to set the velocity function equal to 0 to determine if there was any time when the particle was at rest. Factoring out a t squared, we see that the velocity was at 0 at 2 times, at t equals 0 and at t equals 6. So let's set up a chart and determine what was happening in these intervals, from 0 to 6 and from 6 to 10. We find that the velocity was negative on this interval, then positive on this interval. So when the particle began to move, it moved to the left. At t equals 6, it changed directions and moved to the right until t equals 10. The question is asking, when is the particle farthest to the left? That's going to have to be at t equals 6. Letter B. When is the velocity of the particle increasing the fastest? This is really asking for maximum acceleration. The acceleration function is given by 3t squared minus 12t. But to find maximum acceleration, we'll need the derivative of this function. A prime of t is equal to 6t minus 12. Setting this equal to 0 yields one critical number, t equals 2. So let's use the candidates test to determine when acceleration was maximum. We'll check t equals 0, t equals 2, and t equals 10. At t equals 0, acceleration was 0. At t equals 2, acceleration was negative 12. And at t equals 10, acceleration was 180. So at 10, acceleration was maximum. And that's when the velocity of the particle was increasing the fastest. Here we have another non-calculator example, this one involving a differential equation. Let dy dx equal 2x plus y. Letter A. How do we know that 1 comma negative 2 is a critical point for the function y equals f of x? Critical values have a slope of 0. So if the value of 1, negative 2 and the slope function dy dx is 0, we'll know it's a critical number. So let's find dy dx at 1, negative 2. That will be 2 times 1 minus 2, which is 0. Therefore, 1, negative 2 is a critical point for the function y equals f of x. Letter B. Is the point 1, negative 2 a relative maximum point, a relative minimum point, or neither? Justify your answer. We already know that 1, negative 2 is a critical number, so let's find its value in the second derivative. This will determine the concavity at that point, and from that we'll know if 1, negative 2 is a max or min. The second derivative, d2y dx squared, is equal to 2 plus dy dx. So the value of the second derivative at 1, negative 2 will be 2 plus the value of that point in dy dx, which is 0. That means the second derivative is 2, a positive number. So at 1, negative 2, we have a concave up section of the graph, which means that 1, negative 2 is a minimum value. This example is from the non-calculator section of the 2007 AP exam. Let f be the function defined by f of x equals k squared of x minus natural log of x for x greater than 0, where k is a positive constant. Letter A. Find f prime of x and f double prime of x. First, let's rewrite f of x as k x to the 1/2 minus natural log of x. Therefore, f prime of x will be 1/2 k x to the negative 1/2 minus 1 over x, which can be written as k over 2 square root of x minus 1 over x. Now let's take the second derivative. That's going to be negative 1/4 k x to the negative 3/2 plus 1 over x squared. This can be rewritten as negative k over 4 x to the 3/2 plus 1 over x squared. Letter B. For what value of the constant k does f have a critical point at x equals 1? For this value of k, determine whether f has a relative minimum, relative maximum, or neither at x equals 1. Justify your answer. If 1 is a critical number, then its value in the first derivative will be 0. So let's use that information to solve for k. 0 is equal to 1/2 k times 1 minus 1 over 1, which is 1. This means that 1 is equal to 1/2 k, 2 is equal to k. Now let's determine with this value of k if 1 occurs at a relative maximum, a relative minimum, or neither. Let's rewrite the second derivative with k filled in. F double prime of x will be negative 2 over 4 x to the 3/2 plus 1 over x squared. So f double prime of 1 will be negative 2/4 plus 1, which is 1/2. Since the second derivative is positive at 1, this indicates a concave up section of the graph, which means that a minimum value occurs at 1. Letter C. For a certain value of the constant k, the graph of f has a point of inflection on the x-axis. Find this value of k. A point of inflection has a value of 0 in the second derivative. Let's use this to find k. 0 is equal to negative k over 4x to the 3/2 plus 1 over x squared, which means k over 4x to the 3/2 is equal to 1 over x squared. Multiplying both sides by 4x to the 3/2 gives us k equals 4x to the 3/2 over x squared. This simplifies to 4 over the square root of x. Also, if the point of inflection is on the x-axis, That's going to be at the point where f of x equals 0. Let's use that information also to solve for k. 0 is equal to k square root of x minus natural log of x, which means k square root of x is equal to natural log of x, and k is equal to natural log of x over square root of x. Now let's let this expression equal that expression in order to solve for x. We'll have natural log of x over the square root of x is equal to 4 over the square root of x, which means natural log of x is equal to 4, and x is equal to e to the fourth. When x is equal to e to the fourth, k is equal to 4 over the square root of e to the fourth, which means k is equal to 4 over e squared. Here are the scoring guidelines for that question. There were 2 points possible for letter A, one for f prime of x and the other for f double prime of x. 4 points were possible for letter B, one for setting f prime of 1 equal to 0 or f prime of x equal to 0, another for solving for k, another for the correct answer, and the fourth was for correct justification. There were 3 points possible for letter C, one for setting f double prime of x equal to 0 or f of x equals 0, another for an equation in one variable, and the third for the correct answer. Our last example is from the 2005 AP exam. This question is also on the No Calculator Allowed section of the exam. Let f be a function that is continuous on the interval 0, 4. 0 is included in the interval, 4 is not. The function f is twice differentiable except at x equals 2. The function f and its derivatives have the properties indicated in the table above, where dne indicates that the derivatives of f do not exist at x equals 2. Letter A, for 0 less than x less than 4, find all values of x at which f has a relative extremum. Determine whether f has a relative maximum or a relative minimum at each of these values, and justify your answer. Critical numbers of a function occur where the first derivative is equal to 0 or is not defined. This is happening at 1, at 2, and at 3. But for a critical number to be an extreme value, the sign of the first derivative has to change on either side of the critical number. This only happens at 2. So for letter A, x equals 2 is an extreme value. Because the sign changes from positive to negative, this indicates that it is a maximum value. Letter B. On the axes provided, sketch the graph of a function that has all the characteristics of f. First, let's put in the function values. 0, negative 1, 1, 0, 2, 2, 3, 0, and we don't have a function value for 4. Now let's look at the first and second derivatives to see the characteristic of the graph between these function values. Between 0 and 1, it's increasing and concave down, and at 1, there's a slope of 0. Between 1 and 2, increasing concave up, leading to a non-differentiable point. Between 2 and 3, decreasing and concave down. And between 3 and 4, decreasing and concave up. Letter C. Let g be the function defined by g of x equals the integral from 1 to x of f of t dt on the open interval 0, 4. For 0 less than x less than 4, find all values of x at which g has a relative extremum. Determine whether g has a relative maximum or a relative minimum at each of these values, and justify your answers. G of x is the integral of f of x. Therefore, g prime of x is f of x. G double prime of x is f prime of x. To find the extreme values of g of x, we'll need to see where f of x is equal to 0 or is not defined. This is happening at 1 and at 3. Of course, we need to determine whether the sign of f of x changes on either side of these critical numbers, and it does from negative to positive at 1 and from positive to negative at 3. This means that we have a minimum value at 1 and a maximum value at 3. So the answer for letter C, at 1, a minimum. At 3, a maximum. Letter D. For the function g defined in part C, find all values of x for 0, less than x, less than 4, at which the graph of g has a point of inflection, and justify your answer. Since g double prime of x is f prime of x, we need to see where these values are equal to 0 or do not exist in order to determine whether we have any points of inflection. This is happening at 1 and at 2. But again, we need to see that the sign changes on either side of these values. That doesn't happen at 1, but it does happen at 2. Therefore, for letter D, our answer is at 2, we have a point of inflection. Here are the scoring guidelines for that question. 2 points were possible for letter A, one for finding the relative extremum at x equals 2, and another for finding that it was a maximum value and providing justification. 2 points were possible for letter B, one for points at 0, 1, 2, 3, and behavior at 2, 2, and another for appropriate increasing, decreasing, and concavity behavior. 3 points were possible for letter C, one for g prime of x equals f of x, one for critical points, and one for your answer with justification. And 2 points were possible for letter D, one for x equals 2, and another for the answer with justification. Tip number 9 for the AP Calculus AB exam. If you are asked to justify your answer, think about what needs justification. They are asking you to say more. If you can figure out why, your chances are better of telling them what they want to hear. For example, if they ask you to justify a point of inflection, they are looking to see if you realize that a sign change of the second derivative must occur. Also, in providing this justification, make sure you use mathematical language in doing so. Common student error number 9. Extreme values always occur at places where the first derivative is equal to 0. Not always, as we discovered in this lecture. Extreme values occur at places where the first derivative is equal to 0, as well as at endpoints of an interval. That's it for today's lecture, and that concludes our AP Review unit. Maybe someday you'll see the word soda again. God bless you, boys and girls.